we are now discussing, I just started the video with queso. So the best way to start a video. Oh, queso. Yeah. 5.3 to 5.4. So this will cover the 5.4 to 5.4 reading guide a little bit, just some of the basics here. And there's some good stuff in here, and then there's some stuff that's not really as essential, like some derivations and stuff like that, that if you like that sort of thing, you could take a look at it. For example, like on page 176, there's a whole derivation about how we get from the typical formula for work, which is, whoops, I started to write the formula for force. Come on. Work equals force times distance, right? Okay, so it shows a derivation there that gets us from that to work equals pressure times change in volume. Okay? Which actually I think it ends up being negative. Let me make sure. Yep, negative. Okay? So you don't need to know that derivation, okay? But this formula would be good to use, and I'm going to give you some practice problems on how to use it, okay? But you do not necessarily need that particular derivation. How do you get from here to here? Sorry, hang on. All right, so that's one of the formulas you'd probably need to know, and basically it's a very similar concept, okay? Because pressure is force per unit area. So if we're talking about work being, here's the amount of force we're putting on something over a certain distance. Can you see how that's kind of roughly related to we're putting a pressure on something in a certain volume. We're causing a certain volumetric expansion, okay? So in chemistry, the only kind of work that we ever really talk about is pressure volume work, okay? And that's applicable in situations where a gas is created, especially. Okay, you have a chemical reaction, it makes a gas, it pushes out on its surroundings, right? If that gas is created, it does work on the surroundings by putting pressure on it because you're now making a gas. So that's kind of the idea behind this pressure volume type work, okay? So that's one of the things that's in there. And they give examples using cylinders and moving the cylinders when a reaction occurs. What else? Okay, so enthalpy. Enthalpy is H, okay? And enthalpy is kind of it's a tricky thing to really nail down, okay? But it more or less means heat, okay, in most conditions, all right? So they go through this whole big thing, and you can read it in the book, okay, if you're interested in it, about how H is related to heat, how enthalpy is related to heat. They're not exactly the same thing. But if we're doing a reaction at constant pressure, they essentially are, okay? So at constant pressure, this is really the takeaway that you should get from really pages 175 and I guess 176 if you look at it, okay? But really, at constant pressure, any reaction that's done at a constant pressure, delta H is the same thing as Q, okay? And sometimes they put a little P down here, and all that means is heat at constant pressure, okay? That's just to note. So again, you can kind of look at how they derive all of that, how they come to that conclusion. But what you need to know, most of the chemical reactions we do in here are at constant pressure, right? When would a reaction not be at constant pressure? Well, oh, okay, I see what you're saying. Because as you go up in the atmosphere, the pressure is changing. Okay, I could kind of see that. I was thinking more of a closed container, right? Closed container where a gas is produced, a dry ice bomb. That's not really a reaction, but it's a process that's done not at constant pressure, right? Because as the gas is created, there's a big pressure buildup until, boom, it explodes, right? So that, in that case, we could not say that delta H is equal to Q because that reaction or that process is not done at constant pressure, okay? But anytime you're doing a lab in here, you better not be closing off containers that are producing gases because you will hurt us all, okay? All right? So in here, when we do reactions, we do them open to the air, and the pressure is going to more or less remain constant throughout a class period, right? Now, from day to day, it may be a little bit different, and there's a couple of our labs where that actually does matter a little bit, okay? But for the most part, our reactions that are done in here are going to be done at constant pressure. So you can pretty much say, from here on out, delta H, we're talking about the flow of heat, okay? We're talking about heat change, okay? Technically, delta H is enthalpy change, all right? But I want you to be familiar with that term because you may see the term enthalpy change on the AP exam, and I want you to know what that means. But essentially, we're talking about the heat flowing into or out of the system, okay? So this is where signs become very important, negative and positive signs, all right? If you have an exothermic reaction, so we talked about this the other day, so you've got your system, right? And heat is flowing out of the system. What do you think your delta H for that reaction is, your heat change? You think it's going to be negative or positive? It kind of depends, right? Now remember, the convention is we always look at this in terms of the system. If this is our system, then heat is flowing out of it, right? So that's going to be a negative heat change, okay? If the heat is flowing into the system, if it's an endothermic reaction, then we would say that our delta H is positive, okay? Supposed to be a plus sign. Not very even. H equals T. I don't know what that means. So does that kind of make sense? Heat flowing out of the system, you're going to have a negative delta H. So that's exothermic means negative delta H. That one needs to be firmly in here in your brains, okay? You need to know that really well. That's important. What else do we need to talk about here? Okay, so I guess we could look at sample exercise 5.3 for a second. This would be a good one because it basically just talks about the negative positive thing, okay? So that's on page 176, sample exercise 5.3 at the very bottom. Indicate the sign of the enthalpy change delta H in each of the following processes carried out under atmospheric pressure and indicate whether the process is endothermic or exothermic. Now, why did they say that little part about carried out under atmospheric pressure? Because at constant pressure, delta H equals Q, right? Okay, so the heat equals the delta H at that point. All right, so an ice cube melts. Endothermic or exothermic? Yeah, you got to think about that for a second, okay? But you got an ice cube. You put it on the table. It requires energy to melt, right? To break those bonds. So that is an endothermic process, right? It's absorbing heat from its surroundings, which means delta H would be positive, okay? All right, so for that first one there, letter A, delta H would be positive for an ice cube melting, okay? Letter B, 1 gram of butane is combusted in sufficient oxygen to give complete combustion to CO2 and H2O. We're burning butane. Take a guess. Endo or exothermic? Yeah, if you put your hand next to that flame, it is going to release a lot of energy into your hand, right? Like a lot of energy. So the system is losing heat to the surroundings. So that's a negative delta H. Just general rule of thumb, combustion reactions will have a negative delta H. Okay? I can't really think of any exceptions to that. Okay, so that's 5.3. Not too difficult, right? We should be able to handle that. 5.4. basically all 5.4 is saying is it's introducing you to this fairly simple equation, that if you want to know the delta H for a chemical reaction, if you want to know the overall delta H of a reaction, then you just take the enthalpy of the products minus the enthalpy of the reactants. Okay? Sometimes this will give you a negative number, sometimes it will give you a positive number, but that will give you some value for delta H. Okay? And that's the basic idea there. What else do we need to talk about? Now we're gonna go into more detail about that when we get to sections 5, 6, I think, and 5, 7. Okay. What they want you to know for right now, on page 178, kind of some useful rules here about enthalpy. So enthalpy is an extensive property, and I don't know if we talked about that very much last year, and I don't think you need to know that for the AP exam. I don't remember that terminology being on there ever. But extensive means that it depends on the amount of the substance that you have, okay? So in other words, you burn a mole of butane, you get a certain amount of heat. You burn 2 moles of butane, you get twice as much heat out of that. And that makes sense, doesn't it? Okay? It's amount dependent is all that means, okay? The second rule, the enthalpy change for a reaction is equal in magnitude but opposite in sign to delta H for the reverse reaction, okay? So the example that they give in the book there is they just reverse the reaction from number 1, from rule number 1, okay? So number 1, they're doing the reaction of methane with oxygen, and it makes CO2 and H2O. The delta H for that reaction is negative 890 kilojoules. That's a lot of energy getting released, right? And so they flip that reaction around, okay? So if you take CO2 and you want to combine it with H2O to make CH4 and O2 again, that requires 890 kilojoules of energy, okay? Which should tell you CO2 and H2O don't like to recombine into methane and oxygen, right? That's not the natural way that process really goes, okay? Because you have to force a lot of energy in there to get those things to do that, to rearrange in that way, okay? And then the third rule here, the enthalpy change for a reaction depends on the state of the reactants in the products, okay? So in other words, the first two here have been talking about H2O as a liquid in both of these examples. They said if we were talking about H2O gas instead of H2O liquid, that changes the heat of the reaction, okay? Because it actually takes some heat or releases some heat when a phase change occurs, depending on which direction it's occurring. And we just talked about that with the ice melting on the last example, right? That was a phase change that required some heat, right? So that's all they're trying to say on that part. And actually, they give you the equation for H2O liquid going to H2O gas on page 179. Okay, it takes 88 kilojoules of heat to go from H2O liquid to H2O gas. Now let's think about this for a second. Do you think it takes more or less heat to go from H2O solid to H2O liquid? So I'm doing this instead. H2O solid to H2O liquid. The delta H for that, first of all, that delta H is positive. We already said that, right? Because that's ice melting. Do you think that takes less heat or more heat than going from a liquid to a gas? It should take less, right? Because it's going from a solid to a liquid. You don't really have to completely separate the particles from one another, right? They're able to slide past one another. Okay? So that requires quite a bit less energy. So you would expect the delta H for that process to be lower than 88 kilojoules. By quite a bit, probably. All right, let's look at this one. Do we have time for this one example? Yeah, if we hurry. Got to be fast here. So sample exercise 5.4 on 179. How much heat is released when 4.50 grams of methane gas is burned in a constant pressure system? And it says use the information given in equation 5.18. Okay, So we've got methane gas. So the first thing you'd want to do here is make sure that you have the equation written for this. Now they already gave us the equation. Okay, and the delta H for this one is negative 890 kilojoules. There's a 2 here. Okay, now this equation is telling us something. It's telling us for every 1 mole of methane that burns, we get negative 890 kilojoules of heat. Does everybody see that? So there's a coefficient 1 right here. Oh, I forgot to balance the H2O, didn't I? Sorry. Okay. So for every 1 mole of methane that burns, we get out negative 890 kilojoules of heat. What they're telling us here is we have 4.50 grams of methane, and they want to know how much heat we get out of that process. Okay? So this is just stoichiometry with a little twist to it, all right? It's really not that difficult. So you got 4.50 grams of methane. And what would be a good first step here, probably? Let's change it to moles. That's almost always a good first step. Not every time, but usually. Okay, so let's go to moles of CH4. I'm going to be a little lazy here just for the sake of time, and we'll say that that's 16. Round a little bit. Now, I'm going to go one step further, though. Okay? Now I know the number of moles, but I can actually say in a mole of CH4, I'm going to produce a certain amount of kilojoules of heat, right? And the equation tells us this. It tells us for every 1 mole of CH4, we release 890 kilojoules of heat. So you put negative 890 here. Everybody okay with that step? It's just kind of an extra step. It's weird putting that in your stoichiometry, but that's really what the delta H is showing you, okay? So then once you calculate that, it's going to give you negative 250 kilojoules. So with 4.50 grams of methane, that would give us negative 250 kilojoules of heat. And if we want to check and see if that makes sense, we said 1 mole of methane should produce about 890 kilojoules of heat. Well, is this more or less than 1 mole? It's less because we're taking 4.5 divided by 16, right? So this should be a lower number than the negative 890. Yes, sir?
Well, if it's possible,
you will always be given a number that you can use to figure out the delta H, or you'll just be given the delta H, one of the two. Yep. And for now, you'll just be given the delta H. In a couple of sections, you'll be given some other information that you can use to find the delta H. Okay? That's pretty much it from 5.3 and 5.4. I don't think that's going to be too tough for you guys. All right, see you on